Good morning and welcome to the second week of this course on fluid dynamics and turbo machines. So, we will start with the part B of the first module. The first module is on fluid dynamics. The part B or the second chapter for this fluid dynamics part of this course deals with integral analysis of fluid flow. We have already introduced the integral analysis and the differential analysis for fluid flow in the first chapter. Basically, the integral analysis deals with a control volume of finite size, whereas the differential analysis deals with an infinitesimal control volume, a very small control volume. And the first one, that is the integral analysis, gets an output in the form of gross parameters like the forces, torque, thrust, etc., acting on the control volume, whereas in the case of the differential analysis more detailed parameters are obtained as output. For example, the velocity field, the pressure field. So, let us start our second chapter, which deals with the integral analysis. So, this is the first lecture on the for the second week, for the second chapter. We begin with the definition of this term system versus the control volume, because we will be doing this analysis for a control volume, and we already said that the integral analysis deals with a finite size control volume. So, what actually we mean by control volume? For this we also bring the context of system. So, let us see what is a system and what is a control volume. Now, this is also defined in different books either as control mass, the system is defined as control mass, and also it is defined sometime as closed system, whereas the control volume is defined as the open system. But in our course we will mainly use the terminology as system versus control volume. So, let us give a definition to this. Now, again we consider this flow like we started our first chapter, and we see how the flow is impinging on the plate. Of course, the plate experiences a force in this direction, and then in the direction in the positive x direction, which is the horizontal direction as shown in this slide, and it keeps moving. This is the previous position of the plate and this is the new position of the plate, and then it keeps moving further and further. Now, if we look at this particular part, we see that we can draw some as shown here, we can draw a boundary across the plate. So, this dashed lines actually indicate the boundary. So, this is essentially the system boundary. Why is it called a system boundary? Because the system boundary is such that it does not allow any mass exchange across the boundary. This is true for any system, that there could be energy exchange across the boundary, but there is no mass exchange. For example, in this case, if we consider the plate as a system, then there is no mass exchange across the plate, but there is energy exchange. We can see the result of the energy exchange if we look at the trajectory of the plate, which is shown here. Assuming that these are like snapshots taken at same intervals of time, we can see that gradually the plate accelerates. So, that means a kinetic energy is imparted by the flow to the plate. So, the plate, which is the system here, which is defined as the system here, is actually receiving kinetic energy from the flow and accelerating. So, there is an energy exchange. across the system boundary, but there is no mass exchange. It is not that this mass exchange is only true for a boundary which bounds a solid. You can have also a fluid bounded by a boundary and there is no mass exchange across that boundary. We will see that example. Now, in the same case, if we consider now a boundary as shown by this red dashed line. So, this is essentially the air sticking to the system. So, sticking to the plate here. So, if we consider this as a boundary, then inside this bounds a region across which there is mass exchange. So, this is basically a control volume. So, control volume is a region in space across which there could be mass exchange, of course, there could be energy exchange across the boundary. Now, if we follow this trajectory of the control volume, we will see that we will have the control volume also moving along with the plate for doing the analysis. Now, in this integral analysis, we will be dealing with the analysis of this control volume. We will not deal with the system, we will deal with the control volume across which there is a mass exchange across the boundary. Now, the aim of this chapter is to actually write the governing equation for this control volume. So, that we can write the known equation for a system in the form of a control volume. That is basically the objective of this particular analysis. Say for a system, for example, in a system the governing equation like mass conservation, that mass cannot be created or destroyed. So, this equation is well known. So, for example, if we can always write for a system the rate of exchange, the rate of change of mass with time dm by dt for a system is 0. In fact, this is the definition of a system, that there is no mass exchange across the boundaries of the system, whereas this is not true for a control volume, because across the control volume there is a mass exchange. So, we have to see how to write this equation for a system, for this governing equation for the system, how can we apply this for a control volume. Another well known equation is momentum conservation. So, for example, if we want to find the acceleration of this plate, what we have to do is we have to solve the momentum conservation equation, which says the rate of change of momentum, that is m into b bar, which is a vector quantity for the system, is equal to the summation of all the forces acting on the system. So, by doing this we can find out what is the acceleration of the plate, provided we know the forces acting on the plate. The forces acting on the plate actually can be divided into two types of forces. One is the surface forces, another is the body forces. The surface force is basically the force which acts on the surface of the system, that is on the system boundaries. For example, the pressure can only act on the surface and thereby it produces a force or a normal reaction acting on the surface of the plate. Fb is the body force which acts not only on the surface but on the bulk of the system. So, each fluid or each element or each atom within the bulk experiences this force, for example, gravity force. So, you can broadly divide these forces, summation of forces, into surface and body forces. Now, again the question is how can we write this kind of equation for a control volume. So, this is basically the motivation for studying this particular chapter. So, this is what we already said, that we try to see how to write the conservation equations for the control volume. We know this for the system, but we want to see how we can translate it to the conservation equations for the control volume. In other words, it means that how to write the time derivative of the quantities of a system for a control volume. So, mainly if you see here, the left hand side of the equation, which is a time derivative of mass or time derivative of momentum for the system, if we can write this time derivative for a system in terms of a control volume, then we can rewrite these equations, this governing equation for a control volume. So, that is the that is more precisely what we are looking for in this analysis. Now, another thing before we go ahead with looking at how to write the time derivative of quantities of a system in terms of that of a control volume, let us introduce ourselves with the concept of accelerating control volume. For example, in this particular situation which is shown here, the plate is accelerating, and as the control volume is sticking to the plate, it is also accelerating along with the plate. We want to find out the forces on the control volume. So, this has to remain along with the plate. So, such a control volume, for an analysis of such a control volume, we have to take a reference frame which is on the control volume itself. We have to see by sitting on the control volume what is happening, what are the forces. So, such a frame of reference is called a non-inertial frame of reference. This is a little complicated subject, and we can only discuss about that after we understand how to deal with a fixed or a constant velocity control volume. And if we put the frame of reference on a fixed or a constant velocity control volume, that frame of reference is called an inertial frame of reference. So, we start with this integral analysis for an inertial frame of reference, in an inertial frame of reference. So, this is shown in the figure that we have stopped the plate from moving, and now we have a fixed control volume. We can also extend this analysis to the situation where the plate is moving at a constant velocity, it is not accelerating. If it accelerates, then extra force terms will come, which we have to deal with separately. But if it is not accelerating and moving at a constant velocity, then by making small changes in the case for a fixed control volume, we can do an integral analysis. So, we go to the next slide. So, let us look at the conservation equations for the control volume. So, this is our fixed plate, and this is the fixed control volume in front of the plate. Now, this is the control volume at time t. We can also define this as a system. That means, there is no mass exchange across this boundary. At a certain time, we can define this as a system. Now, the second box, the second region, which is shown by a bounding surface with black dashed line, this is the system at t plus delta t. Delta t is a small time, small period of time. So, if we look at the system boundary, what would have happened because of the flow, the mass which was here, the flow fluid particles which were in this region has moved into region nearer to the plate, and some fluid particles have moved out of this control volume in this region. So, basically this is the system at t plus delta t. So, as we can see here, which we have mentioned in the last slide also, that we can define a system even for a fluid, not necessarily only for a solid. Only the mass within that region has to be constant, and it has to be the same mass. It has to deal with the same mass at all point of time. So, we define this kind of a situation that we have a control volume. The control volume does not, it is a fixed control volume, it does not move with time, but the system, just to keep its own definition, that the mass within the system remains the same at all point of time, it has to move. But the control volume at time t plus delta t is again shown by this red dashed line. Now, this is this was to show for this simple case, we can take this in a more look at it in a more generalized control volume. So, let us consider this is a flow, this is a arbitrary flow, and we define a control volume within this flow. So, this is shown in like a oval shaped control volume, it could be of any shape. Now, this is the boundary of the control volume or the control surface at time t, or this is again defined as the system at time t. So, now after a point of time delta t, that is at time t plus delta t, we see that the system has actually moved to a new position, because it has to keep the same fluid particles at it as it had at point of time t. So, it has to move with the particles, it has to move along with the particle. So, it is now in this new position. The control volume actually is in its same position. Of course, the properties of the control volume changes. For example, the mass of the control volume can change. Now, let us see how to write the time derivative of quantities in this control volume shown here. So, this is a system at t plus delta t, and the system at t which is same as the control volume boundary, which is same as the control volume region. Now, let us also define a variable b. So, this is a general variable, so that we can apply it to time derivative of any quantity. So, this general variable could be mass, momentum, angular momentum, anything, but for that we make it a general variable and find out what is the time derivative of this quantity b, or what is the time derivative of b for a system in terms of the control volume parameters. Now, we also define this parameter beta, which is b per unit mass. That means, this variable the same property per unit mass. For example, if we are defining momentum, then this is beta becomes velocity. So, this is the question, how to write dB by dt of the system for a control volume or in terms of a control volume. So, we write dB by dt of the system from the basic calculus. We know that we can write a derivative as a limit of as delta t tending to 0 b system at t plus delta t minus b system at t divided by delta t. So, basically this is what we can write the expression of a derivative from first principle. So, whatever b is there at time t plus delta t within this boundary minus what was there at time t divided by delta t is the time derivative. Now, what is b system at time t? It is same as whatever b was there in the control volume at time t, because the system and the control volume are one and the same at point of time t. Now, what we do is to look at b system at time t plus delta t. We divide this entire region into 3 parts. First part is 1, second part is 2 and third part is 3. So, this entire region which has the first control volume, the first system at time t, the system at time t plus delta t and their intersection into 3 parts. So, part 1 is a subset of basically the control volume or the system at time t, but it is not a subset of the system at time t plus delta t. That means, it is only this region. So, this region is basically the region bounded by this control surface by red dashed line and this black dashed line. The second region is the common region between the system at time t plus delta t and time t. So, this is basically the intersection of these two position of the same system. Okay. So, this is bounded by this line, this black dashed line and the control surface boundary, and the region 3 is the subset of system at t plus delta t, but not that of the control volume. So, this is the region bounded by this black dashed line and the red dashed line here. So, in other words, this is like this region 1 is like whatever has come into the control volume at during the time delta t, the property of that. If b is a property, then b of that quantity, or this is the region which has moved into the control volume in time delta t, and this is 3 is the region which has moved out of the control volume at time delta t at during the duration delta t, and the region 2 is the time is the region which has remained within the control volume during the duration delta t. So, one is the first part which has entered into the control volume from somewhere else into somewhere else, and 3 is the region which has gone out of the control volume during the time delta t, and 2 is the region which has remained within the control volume during this duration. So, we divide it into these 3 parts. Now, this makes us easy to define the value of b for the system at time t plus delta t. So, it is given as this. So, value of the variable b for the system at t plus delta t. So, system at t plus delta t is actually shown by this black dashed line. So, value of b for that will be value of b in this region 2, which is remained within the control volume, plus value of b in the region 3, that is the region which has come out of the control volume. So, that constitute of the value of b, variable b for the system at time t plus delta t, b 2 plus b 3. Of course, b 1 will not come here, because b 1 is something which has entered the control volume during the time delta t. So, it is not a part of the system. The system can only have the same fluid particles at all instants of time. So, that we have to always keep in mind. It has to keep the same mass, same fluid particles at all instants of time. So, one cannot be a part of it. So, it is b 2 plus b 3. Now, you can write b 2 as b for the control volume at t plus delta t minus b 1. So, you can indirectly write it in terms of b 1 as the total value of b within the control volume at time t plus delta t, which could be different from the value of b at time t, because control volume, the value of this variable b, which could be mass, momentum, angular momentum, anything. So, the value of that quantity at time t plus delta t within the control volume will constantly change. So, this b c v at t plus delta t minus b 1. So, b c v at t plus delta t is this region minus b 1 which has entered into the control volume, that will of course be b 2 plus b 3. B 3 is what has gone out of the control volume. So, now by writing it in this form, if we can plug in these two components here, what do we get? We get the limit of delta t tending to 0, this is the numerator and divided by delta t. So, what we see here is basically the value of b c v at t plus delta t and b c v at t appears in this expression. So, this helps us to write expressions in terms of the control volume. In the sense, if we club these two parameters like b c v at t plus delta t and b c v at time t, then we can write a expression like this, which is very similar to the time derivative like we have shown here. So, this is the time derivative from the first principles, and this is the rest of the term, which is b 3 minus b 1 by delta t. We will see how to deal with this second part of this expression, but right now we can directly write this as partial derivative of the quantity of b in the control volume with respect to time. B in the control volume could be dependent on time and space. So, we write it as a partial derivative. So, partial derivative of this quantity b c v with respect to time plus this second quantity. Let us see how to write the second part of this equation now. Because we have partially written, what we wanted is to write the time derivative of a parameter b for a system in terms of that of a control volume, b for a control volume. We have partially succeeded in that. Let us see how to proceed further and deal with the second part of this expression. So, we come to the next slide. Again we have kept the same figure to take help during the derivation. So, this is dB by dt of the system, we already derived it. This is already derived part, but we can write BCV actually. So, this let us see what is the value of BCV. We can write it as volume integral. So, this is integral over the control volume of the quantity beta rho into dV. So, this v small v is basically volume. Now, if we see rho into dV is basically the elemental mass within the control volume, because the integration is done within the control volume, and beta is the B per unit mass. So, B per unit mass multiplied by elemental mass, if it is integrated over the control volume, will give the total value of B in the control volume. So, that is how we get this. We can plug in this here and then make it more descriptive in terms of the control volume parameters. Now, what is the second, how to deal with the second part? The second part, the first term in the second part is B 3, of course delta t comes in the denominator. So, B 3 can be written in this way. So, this is a surface integral. We have just directly written this expression. Now, we will try to see how this expression is obtained. So, if we look at this expression, this term is again something similar to the term here. So, this is also a volume. So, this is what volume is this? This is actually volume of an element in region 3. So, we are talking about B 3. So, this pertains to region 3. So, this is volume of an element in this region 3. So, let us see it in little more details. So, of course, if we if this represent considering that this represent the elemental volume in region 3, then multiplying that elemental volume with density will give you elemental mass, which multiplied by B beta per unit mass will give the value of B, and if it is integrated everywhere within this region, then you across this region CS 3, then you get the value of B 3. Now, let us see how is that this is a volume. So, we take an elemental volume like this. Now, we take out this volume and reproduce here to look at the different velocity and areas appearing in the expression. So, the velocity if this represent the streamlines, then the tangent to that will be the velocity. So, the velocity vector will be oriented like this, and it is not necessarily oriented perpendicular to the control surface. The red part is basically the control surface taken out from here, and this is not necessarily oriented normal to this surface. So, what is oriented normal to this surface? This vector is basically the area vector. So, this is ds bar. So, ds bar is always in this convention and in many books also you will find that the general convention is the area, positive area is oriented outward. Of course, the direction of the area of any surface area is the direction of the normal to the surface and oriented outward. What is the meaning of this outward? Outward means, so this pertains to a control volume. So, there is a region inside the control volume. The area vector will not orient itself towards inside of the control volume, it will orient itself outwardly from the control volume. So, for example, if you go to this side, we will see it soon that this side it will be oriented opposite to what is shown here, it will be in the other direction, normal in this direction. So, anyway, so if you now consider this, then velocity in general in a generalized form is not oriented along the normal to the surface, control surface, and there let us say the angle between these two vectors is alpha. Then the component of velocity along this normal is V bar, magnitude of V bar cos alpha, and if you multiply that with the time duration delta t, what you get is the distance travelled. So, this is basically the length of this control volume. So, if you now see this as the distance, and if we look at the volume now, so the shaded volume will be given as V bar into ds bar cos alpha delta t. So, if you bring the magnitude of area here, then you get the shaded volume. So, volume shown in this region or shown in this region. Okay, so, this is basically in terms of cos alpha. You can generalize in a generalized way, you can write it as V bar dot ds delta t. So, that is how you get this expression V bar dot ds delta t, and if you multiply this with density, you get elemental mass, which with beta multiplied with beta gives the value of B in the entire volume in the entire region 3, and this has to be done over where it has to be integrated, it has to be integrated over CS3. What is CS3? CS3 is basically the control surface of the control volume which is shared with the region 3. So, in this figure it will be like this. So, the control surface shared with region 3. So, for example, now if you sum all this, we take this simple example. So, we sum all this volumes, we will get the volume of this entire region 3. We have to keep in mind, although it is shown in a little exaggerated way in this figure, but this displacement is actually very little because the time which we have considered is a elemental time delta t. Okay, so this basically shows us how we get B3. B3 is basically integrated value of beta into the elemental mass, rho into the elemental volume in this region, in the region 3. So, and CS3 is basically the part of the control surface means the part of the surface of the control volume CV shown by this red line, which is shared with region 3, that is shared with the exiting part, or you can say this is basically the part through which the fluid is exiting the control volume. So, this is B3. Now, in a similar way you can find out B1, because this is the next parameter to be found to get an expression for a complete expression for dB by dt for a system. For B1, so what is the difference between B3 and B1? B3 is basically the region which is coming out from the control volume, and B1 is the region which is entering the control volume being shown as the red dashed line. So, B1 is what is entering into the control volume. So, now for B1 we can again write a similar expression like beta into this is the elemental mass now, which can be obtained from a similar analogy like this, similar explanation like this, and so this is a typical elemental mass here. So, we have shown the elemental volume here. So, this is the elemental volume. There is one difference here, see there is a negative sign if you have noticed as compared to the previous expression. This B3 has no negative sign, but it has a negative sign. Why this? Where from this negative sign comes? This comes from the fact that if we look at the velocity vector now, the velocity vector is oriented because this is an inlet, the fluid is coming into, so this is an inlet, so the fluid is coming into the control volume through this surface. These are all the surfaces through which fluid is coming into the control volume. So, the velocity vector is directed like this, but the area vector is directed in this way. So, this is true for all the surfaces, all the regions of the control surface through which the fluid is coming into the control volume. So, if you do a V bar dot ds between these two vectors, it will be negative because the angle is more than 90 degrees. So, it will be negative. To compensate for that, this negative sign is introduced. So, now we can, if we incorporate this value of B1 and this value of B3 into this expression, then we get an expression like this. You can see delta t will get cancelled out from the numerator and denominator as it appears here. So, you get because of this negative sign, now it can be written as this was the first part is written by plugging in the value of BCV, that means the value of the variable B within the control volume, a partial derivative of that, and the second part has these two terms. The first term pertains to the value of B, the sum of the value of B which exits the control volume through the exiting surface, that is CS3 control surface, and this is what is coming into the control volume through the incoming surface. This can be actually written together because CS1 like we have written here and here, it is this region, it is this surface through which fluid is coming into this control volume. So, if you see this part CS3 is this region through which fluid is going out of the control volume. This part is same, this expression is same in both this integral. So, you can club this and you can do a cyclic integral over this control surface itself. So, you can write it as partial derivative of this and a cyclic integral over the control surface of this quantity. So, that means you have, to begin with, you had the time derivative of a quantity B for the system, whereas you have written it as the time derivative of the same quantity in the control volume and the time derivative of the same quantity on the control surface in terms of the integration of the quantities on the control surface. So, let us get an idea about the physical meaning of this expression which we have obtained. The first term is basically the rate of change of B in the control volume. So, this means that let us take an example of mass. It is easy to visualize that. We say that dm by dt for a system is 0, because the mass does not cross the system boundary. But here if you see this, in that case this will become del t of m, mass of the control volume. This is not necessarily 0, even though this is always 0 if when we take B as mass, but this is not necessarily 0. So, that means the mass in the control volume is changing with time. And what is this parameter? This parameter is basically net rate at which B exits the control volume through the control surface. So, for this specific example of mass, this is the net rate at which mass exits the control volume through the control surface. The term exits also accommodate inlet, because inlet will mean a negative value of this parameter. So, now let us see if it is not negative, if it is positive. So, what does it mean? That the mass is exiting the control volume. The control volume is actually shown by this red dashed line, and rate of change of, there is a rate of change of mass of the control volume which is shown by the first part, and the second part is essentially the net rate at which mass exits the control volume through the control surface. So, if it is positive, it means the rate of change of mass has to be negative, because if this quantity is positive, then and the sum of this two is 0. Okay. So, rate of change of mass plus net rate at which the mass exits the control volume, that is equal to 0. So, rate of change of mass will be negative, which is also true if the net rate of mass exiting the control volume is positive. That means, mass is on the net flow, if you consider, it results in a loss of mass from the control volume, and so the mass of the control volume will decrease with time. Similarly, if this is negative, if this quantity is negative, it means that dm by dt of the control volume, this is essentially dm by dt of the control volume. If we consider B as the mass of the B as a parameter like mass, then rate of change of mass of the control volume will be positive, because this is a negative quantity and this minus this will be 0. So, that means if there is net inlet of mass within the control volume, the mass of the control volume will increase with time. So, that also makes sense. So, the statement of this expression is very simple. Of course, there is a mathematically rigorous way to get to this expression, to make it applicable to a very generalized situation. So, basically the statement of this particular expression is actually stated as the theorem called Reynolds transport theorem, and this equation is called Reynolds transport equation. So, again just to repeat, the Reynolds transport equation converts the time derivative of any quantity for a system to an expression for the similar expression for a control volume, and time derivative of any quantity for a system in terms of control volume can be written as a summation of two particular terms. The first term is the rate of change of that quantity in the control volume, and the second term is the net rate at which that quantity exceeds the control volume. So, basically that is the Reynolds transport theorem. So, in this lecture, this is the first lecture for the integral analysis. What we did is we started with the definition of system and control volume, and we know that the governing equations for the system, all the equations are well known. The task of this analysis to begin with is to write the similar equation or translate the equations for a system to that of a control volume. For that, what was essential was to write the time derivative of any quantity for a system in terms of that for a control volume. So, we did the derivation of that, and we basically came to the end of at the end of this lecture, we came to the expression for the Reynolds transport theorem. In the next lecture, we will apply the Reynolds transport theorem to some specific case for conservation of mass and momentum. Thank you.